SolidWorks simulation, lecture 16, flow simulation, part 3, cooling of electronic device. First of all, we will load the software, SolidWorks flow simulation, and load the toolbar, the main toolbar of flow simulation, and open the project. And the procedure requires that we define the boundaries for the flow system. So we choose these surfaces to create the lids or covers so that the boundaries of the flow system will be defined. And we created 4 lids. The lid 1 through lid 3 will be the outlet surface, and lid 4 will be the inlet fan. And we have finished with the first step of flow simulation, which is drawing of a 3D model and open a case and also generate the lids. For step 2, we use Wizard for the initial condition, project name, units, and in this page we'll check the heat conduction option, and the flow direction will be X direction, so we don't change this. So in this page we only check the heat conduction option, and for default fluid we use air as a default fluid, and the default solid will be aluminum alloy 6061, and the wall will have heat transfer, and the coefficient of convection heat transfer will be 40. You can enter 40 through 60, and the ambient temperature or room temperature will be 20 degrees C, and the initial temperature and pressure will be 1 atmosphere and 20 degrees C, and these are for the external flow system, so we don't have to use this right now. Before we finish with the second step, we go back to see what we did. We click next, and choose this heat conduction in this problem, and make sure the flow direction is in the direction indicated here. And the default fluid will be air. Default solid will be aluminum alloy 6061, and the wall will have heat transfer, and the coefficient of convection heat transfer will be 40 watt meter square K, and the ambient or room temperature will be 20 degrees C, and the initial condition will be 1 atmosphere pressure and 20 degrees C. And then we have finished with the second step. For the third step, we will define a fan here. So we'll insert a fan. We'll insert in flow simulation. In flow simulation, we'll insert a fan. And in this surface, make sure that it is inner surface instead of outer surface, because you always choose the surface in contact with the flow. And choose the predefined axial fan and JMC 7000 series. Here, 12H, 7015 12H. And we choose this fan as the inlet fan. Now for the outlet, we'll choose these 3 surfaces and insert a boundary condition for the pressure, environment pressure of 1 atmosphere pressure and 20 degrees C. So this is the outlet condition, boundary conditions. So there are 2 boundary conditions that are defined. The first one is inlet fan, and the second is the outlet atmosphere pressure. And before we proceed with the next step, make sure that we have the heat source defined. So there should be a CPU underneath, but I omitted the CPU. So we'll heat the bottom surface of this heat sink. So I'll choose Tool, Flow Simulation, and in the flow simulation, I'll choose Insert Surface Source, because I didn't define the volume of a CPU, so I use Surface Heat Source. And the surface is the bottom surface of the heat sink. And the value will be 28 watts. Actually, it should be 28 watts, but in this problem, I'll make it 100 to make it hotter. So higher temperature, so it is easier to see. But make sure that it is you have to enter the right amount of heat generation here. So it is actually 28, but I rather give it 100 watts on this surface. Okay, so we have finished with the third step, where we define the inlet fan and outlet surface of atmospheric pressure and also the heat source. So these are the third step that we have done. Okay. So now for the goals, I'll enter a global goal for pressure and velocity, and also the temperature of solid and fluid. So these are the global goals. And also I'll define surface goal. For example, if I want to know the values on this surface, so I'll let it calculate the pressure, temperature, and velocity, and also the solid temperature on this surface. So you can also define the goal for the inlet surface and outlet surface, and then you can run the procedure. And I'm going to stop recording because it take quite a lot of time running this procedure. Okay, now the solver has finished, so we can generate, first of all, generate the car surface or car plot for the pressure or velocity on the XY plane. Okay, so we generate a car plot for velocity, and we can play with the animation of the velocity field, and also we can edit as a pressure or temperature plot, and also play with the car plot, so we can see that the temperature of the flow field, and this will be the temperature field. So if we stop the animation, and we can redefine the heat sink and make it transparent, so we can see the temperature. So we can first of all, you need to let the heat sink transparent, so you can see the temperature change. So now we'll play again the temperature distribution, right? So you can play. So now you see the temperature distribution of the flow system. Okay. Now you can always play with all the values. You can see the temperature is highest on the heat sink. So now I'll hide the car plot. We can also play with the flow lines with the inlet surface and outlet surface chosen. And we can display the flow line in lines with velocity as the color and using 40 lines. So you can see that this is the flow line. So you can play the flow trajectory. So this is the trajectory. You can also change the lines into arrows and make the arrows larger, 3 times larger. So you can see that in the animation, the velocity of the air at the inlet rotates, and it cools down this heat sink and then flow out through the outlet. So this is the lecture 16 part 3, the cooling or heat air cooling of electronic device.